They need to agree to be recorded. Thanks.
Okay. So thanks for the introduction. As David said, so I work at the Space Telescope Science Institute, which is where both the flight and science operations of JWST are coordinated. I actually work for the European Space Agency, so I'll try to talk a little bit about how that works. So I am basically part of ESA's contribution to the mission. And I'm based full-time at the Institute to support the operations of the mission, and specifically the MIRI instrument, so the mid-infrared instrument. This is the instrument I've worked on since 2008, since well before I joined ESA. It's basically my whole career. So I'm going to give you a bit of kind of an overview of the early days, not the early days of the project, but kind of since the launch. And the kind of things we did in commissioning, results we got from commissioning, show you some nice data, and then talk a bit about the things that we've been doing in the last few months since the end of commissioning. David told me you're all very interested in engineering, so I will try to highlight some of the cool technology and everything, but feel free to ask me more questions at the end.
I may have been projecting. But I'm convinced that they're supposed to be interested in engineering.
So the James Webb Space Telescope, JWST, launched last year on Christmas Day. I was one of the very lucky few who got to travel down to Kourou to watch the launch, which was a pretty amazing experience. This is not a picture I took, of course. I watched the launch from about 3 miles distance, which is about the closest that you can get. But if you ever have the opportunity to go to that part of the world, and in particular ever have the opportunity to visit the Arianespace spaceport down in French Guiana, please do. It is an extremely impressive facility they have down there. So basically this is a country that's for about 98% covered by virgin rainforests, and then there's like a tiny strip of land along the coast where people live, and then a huge part of the economy is all kind of dominated by the Arianespace site there. So they have various kind of launch sites for different rockets, and huge amount of kind of assembly facilities. Also amazing safety briefing, because it's basically like a munitions depot. They have huge stores of rocket fuel on site. So if most of your health and safety type briefings have been quite boring in your life, I highly recommend one of those, because it's basically like 2 hours of all the ways you could die. So as you know, the launch was extremely successful. The launch was was ESA's big contribution to the mission. So the launch was on an Ariane 5 rocket. Went absolutely beautifully. This was the last view that we got of the telescope as it detached from the rocket, and we kind of watched it disappear out to its orbit at L2. Very soon after this, we saw the solar arrays deploying, which was a really good sign. To talk a bit about the various agency contributions, as I work for the European partners, I always like kind of showing this. JWST is a collaboration. It's led by NASA, but has involvement from ESA as well as CSA, the Canadian Space Agency. And this graphic kind of shows you where those different contributions are. You said the mics are in the ceiling, right? It's fine if I walk around.
Yeah, come on around, yeah.
So everything in red here is European contribution. So the entire launch segment we have here, the launcher, all the launch site services and the payload adapter, all the work that needed to go into the Ariane 5 rocket to make the launch happen is all provided by ESA. Obviously also with Arianespace staff in there as well. The observatory segment is a kind of mix of different partners. So the spacecraft, the telescope, all provided by NASA. And then on the instrument side, we have 4 science instruments. NIRCam is entirely American. MIRI is 50-50 European-American. MIRIS and the Fine Guidance Sensor FGS are Canadian. That is the Canadian contribution to the mission. The NIRSpec instrument is entirely provided by ESA. And then on the ground segment, the majority is all provided by NASA, so the Operations Center at STSCI, is a NASA contractor facility. All the communications through the Deep Space Network is all NASA. But then we have this kind of contribution, a team of 15 ESA personnel. So it's not necessarily staff members, it's 15 ESA funded FTEs, as they say. And so I'm basically one of those 15 FTEs. So I'm kind of part of the European contribution to the mission, and that's really to ensure that the expertise that was built up over the years in Europe kind of gets, moved or kind of transferred, is what I was looking for, from Europe to the United States, and that we maintain that connection back to Europe as well. So JWST is not in low Earth orbit like the Hubble Space Telescope or other missions. Webb operates out at the second Lagrange point. So this is a sort of quasi-stable point in the gravitational system between the sun and the Earth. So this is about 1 million miles, 1.5 million kilometers from the Earth, kind of along the line from the sun to the Earth, but kind of behind the Earth. So as the Earth moves around the sun, Webb and Webb's orbit will travel along with it. There are other space telescopes already there as well. The Gaia mission, for example, which I know some of you work with, also operates out at L2. What's really nice about being at L2 is, first of all, we're kind of shielded from the sun by Earth, so we're always along that line. Also, if you're in low Earth orbit, you are for half of the orbit in the sun side of the Earth, and so that affects your operational efficiency. You lose that time, whereas out at L2 you can operate 100% of the time. And in addition, that kind of the low Earth orbit would just never have worked for an infrared telescope, because that sort of constant thermal change would have been very detrimental to the performance.
It doesn't have solar panels?
It does have a solar panel, yes. So we do have a sun side, the sun pointing part of the telescope, but it is partially shielded, so it's not like full in the sun.
I guess the bigger point is not that you're hidden from the sun, it's that your sun illumination is constant.
Right.
If you were in low Earth orbit, you'd have varying sun illumination.
Yes, correct.
But are you always in the shadow of the Earth?
You're not like full in the shadow, but you are kind of partially shielded, yes. I'd have to look at that myself, because I sometimes wonder that too, but yes. In terms of the field of regard, it's kind of this is the big sun shield. I'll show more views of what the telescope actually looks like. But so this large structure is the sun shield, which is like about the size of a tennis court. So that the sun is kind of always over here, so that the sun shield is always shielding the telescope from the sun. And then you do have sort of communication hardware solar panel kind of on this side of the sun shield. So you have some degree of freedom kind of along this axis, and then the telescope can also kind of rotate by 360 degrees. So you constantly have, at any given point, at any given time, you can see about 39% of the sky with JWST in this annulus shape. And so as we travel through the orbit over the year, the annulus sweeps by about 1 degree per day, so that over the course of time you do cover the entire sky. The visibility, what Webb can look at any given time in its orbit, depends on the ecliptic coordinates. So the higher the ecliptic latitude, the better the visibility tends to be. So you see here a right ascension and declination map. So the background image shows the galactic extinction map, with the curves of kind of constant ecliptic latitude overlaid. And so below -85 latitude and above 85 in the north, you have 2 continuous viewing zones where any objects that are in there can be seen all year round, basically, with JWST. The southern CBZ contains much of the Large Magellanic Cloud. So during commissioning, we spent an awful lot of time in the Magellanic Clouds. That's where a lot of our calibration fields were, because we would, because that was visible at all times for us. A lot of the early data was from Magellanic Clouds. Communication to the observatory is done through the Deep Space Network, which is kind of NASA-managed network of dishes all around the Earth. Specifically, we work with 3 dishes, Canberra, Goldstone, and Madrid. So throughout the day, we sort of hand over between these stations that manage the upload of schedules or commands and download of data. We have 2 contacts. So during commissioning, we were in full-time contact with the spacecraft, so we could really kind of be in touch with it at all times and download data very quickly. Now in routine operations, we have 2 contact times per day where we download new data and upload schedules or commands. And then through the Deep Space Network, we relay with the Space Telescope Science Institute, where all the flight ops and science ops and the data archive is all based. We have 4 science instruments on the telescope. So I won't go into all of the different capabilities in too much detail in the interest of time. But so we have.
Can you go up and mute, go to participants and mute?
Yeah, I was just gonna say. And then you might need to unmute yourself. Oh, you're unmuted. You're good. You're good. Good. Thanks.
So I already highlighted these instruments showing the different partner contributions. So in the top left there, we have the NIRCam instrument. NIRCam is the kind of workhorse imager for the observatory. It was led from the University of Arizona and built in collaboration with Lockheed Martin. NIRCam is, as well as being, a science imager, is also the instrument that was used to align the telescope and monitor the wavefront in operation. So in that sense, it's hugely important, and it was also the earliest to be switched on and commissioned because we needed to use it for the mirror alignment and phasing. To that end, because it's so important, NIRCam is actually fully redundant. It has an A module and a B module that are virtually identical. So very much so that if there was a problem with NIRCam, that there was basically a full second copy of it on board so that we would still be able to use the mirror. And that's kind of a big theme with all of the instrumentation and hardware, is that there is a huge amount of redundancy. Every electrical circuit has a backup, basically. So everything is on board in duplicate. NIRSpec is kind of NIRCam's spectroscopic counterpart. It's a European instrument built in collaboration with Airbus in Europe, and that is a near-infrared spectrometer. It has various different ways of doing spectroscopy. It has an integral field spectroscopy mode. It has simple fixed slit spectroscopy, and also a multi-object slit, a multi-object spectroscopy mode. So where you can overlay a grid of tiny little windows, basically micro shutters, these tiny little MEMS devices that you can then map onto a field of galaxies or of stars, and open the ones that you want and leave shut the ones that you don't want, to kind of get spectra of a few hundred targets all in one shot. The MIRI instrument, so this is the one that I've been working on, and so there'll be a bit of a MIRI bias in the rest of the talk. Has quite a different consortium structure as well. So we have 50-50 European and US. On the European side, we have a big consortium of 10 partner countries whose own national agencies funded the construction of the instrument. And also in the US, our collaborations were with JPL mainly and the University of Arizona. The fourth instrument is NIRIS and the Fine Guidance Sensor. So this was Canada's contribution to the mission. So Canadian Space Agency in collaboration with Honeywell. The Fine Guidance Sensor in particular, very important because it is basically It's how it enables the telescope to maintain pointing on a target and guide. So very important for the scientific operations of the observatory. You see here a bit of layout showing important components. So here's this multi-layer sun shield that actually consists of 5 very thin layers of material that shield the telescope from the radiation of the sun. The big primary mirror, which is segmented, consists of 18 hexagonal segments coated in gold. The material of the segments is beryllium with then a gold coating on it. Gold is the best for reflectivity in infrared. On the sun side, you have the solar power array, the high gain antenna that points back towards Earth for communications, the spacecraft bus, star trackers, and then on the cold side, you have the telescope, the primary, the secondary mirror assembly, and on the back there, the instrument module, which I'll show. Yep, right there.
And the trim flap that you showed there, does that do?
I think that's a
solar
momentum.
torque? Is it momentum?
Might be a momentum thing, yep. So here you can see kind of an animation of how the instruments are packed into the instrument module, ISIM, the Integrated Science Instrument Module. So yeah, so it goes transparent, and then you can see you've got NIRCam in the middle, and NIRIS also kind of packed in there in the middle. MIRI is on the side there, and the big one is NIRSpec. This is what the full focal plane of the telescope looks like. So each instrument occupies its own position in the large focal plane, and that is sort of constant. So that layout is constant. So you see NIRCam right at the center, which is used to really phase and align the primary mirror, and then you've got the others dotted around. So you can operate multiple instruments at the same time, but you're not looking at the exact same part of the sky, so they're always kind of separated. A big part of our initial calibrations when we started, with commissioning, was to exactly define the coordinate system, how these instruments are all kind of laid out to make sure that we can point very accurately and we understand where we are pointing at all times. I'm going to talk a little bit more about MIRI because I will be showing some data and some science from the MIRI instruments. So there's 3 instruments that cover near infrared wavelengths. There's only one that covers the mid-infrared. So we try to do kind of everything. So MIRI has a lot of different capabilities on board. We cover from 5 to about 28.5 microns. And the project was led by Gillian Wright from the UK Astronomy Technology Centre and George Reiki at the University of Arizona. We have a regular imaging camera, which has, I think, 9 imaging filters ranging from 5 to 25 microns. We also have coronagraphic imaging. So this is where we block the light of a central star to be able to image structures around it, like disks or planet companions or brown dwarf companions, with some different designs optimized for different wavelength ranges. We have a low resolution spectrometer, which covers 5 to 12. Actually, it covers 5 to 14, I can say now, which is the mode that I've been leading for a decade or so. And then we have a medium resolution spectrometer that has a resolving power of about 3000, which is an integral field spectrograph. So it basically has a very small field, but it disperses the entire field. So the product from that is you kind of get a cube, you get the entire field of view, but stacked along the wavelength axis. So this is an incredibly powerful mode of observing. You get a huge amount of information from the whole field. All of our modes, the imaging LRS and MRS modes, can actually be used in time series observations mode. This is specifically to look at particularly transiting exoplanets or other kind of time variable phenomena where you want the sort of a fixed cadence or time resolution. And so this is, again, a good fraction of our science program is looking at exoplanets with the view to kind of characterizing their atmospheres. The low resolution spectroscopy mode is the most specialized for that type of observation. So it's a fairly large fraction of my time is spent on that. Also unique about MIRI is that we are the only actively cooled part of the observatory. So in general, the observatory is passively cooled, so we just allow the heat to radiate away. And so the main operating temperature for the observatory is about 40 Kelvin. But at the mid-infrared wavelengths that MIRI covers, at that temperature, the detectors have way too much dark current and are basically not usable. So our detectors have to be operated below about 7 Kelvin. And so our entire instrument is actually designed to operate at that temperature. So we have a cryocooler on board just for MIRI, just to cool MIRI. And this was actually one of the kind of higher risk and more innovative parts of the observatory. So there was a lot of development that went into building the cryocooler, and this was entirely done by JPL. The design, the kind of optomechanical design and thermal design of MIRI was also really kind of adapted for operating at that very low temperature. So all of our design was really focused on avoiding any unnecessary heat loads, so minimizing the number of mechanisms we have in the instrument. We don't, for example, have decontamination heaters that the other instruments have. So this is where, as you cool down, there is a risk of molecules freezing onto optics and causing contamination. So of water, for example, you would get sort of a layer of water ice on your optics. And a lot of instruments would have small heaters at key components that they can kind of evaporate those contaminants off. We don't have that, so we had other aspects of our design that were that specifically were put in place to avoid contamination. We have, for example, a full kind of contamination control cover, which was specifically designed to keep contaminants out. We also have very careful thermal isolation from the rest of the instrument structure to keep all that 40 Kelvin heat off of MIRI. The cryocooler is a kind of multi-stage. It has quite a few different technologies on board. It's a fully closed system, so we don't have a consumable helium or anything. We don't run out of helium. And what's kind of special about it as well is that it's a lot of the hardware of the cryocooler is actually quite far away from the instruments. So the hardware is all distributed around the observatory, and we have about 20 meters of refrigerant lines running all through the observatory. So normally that would be maybe, centimeter, you might have centimeters or half a meter or something, but in our case, it's a huge system that runs throughout the observatory. It took, because we had to cool actively with MIRI, it actually took more than 100 days after launch for us to actually reach our operating temperature. So a lot of the other instruments had gone quite a way through their commissioning plans already by the time that we even got to open our contamination control cover and look at the sky. The first few months of commissioning, we did a lot of sitting around and watching temperatures drop, basically. And then at the end, in the final month, to get all of our data in the space of a couple of weeks. So we had a very interesting timeline in that sense. Yeah.
I'm just amazed that you can make a closed loop cryogen system that can survive the vibration from launch without leaking.
Yeah. Yeah, so that was, it's there was a huge amount that went into the cryocooler. Like I said, it was one of the higher risk elements of the observatory at various stages. It was on the critical path, I believe, but yeah, and it's working beautifully. Yeah.
And before launch, they shake the hell out of it before launch, right, to check that it survives the shake? Yes,
absolutely. Yeah. There was at various stages we did vibration tests. Yeah.
Is that technology being fed back into the cryogenic, like various cryogenic industries? Because it seems like a better way to do things.
I was not very closely involved with the cooler development, but yeah, I would imagine so. Yes, yeah. It's also one of again the cryocooler had its own team supporting during commissioning, and we also kept a very close eye on whether the cooler was, because we also wanted it to be a very low vibration system because we didn't want it to cause jitter in other parts of the observatory. So that was also a really big part of it, is kind of monitoring whenever, when we had to step up the cooler power at various points during the cool down, is really monitoring how this impacted the other instruments. And, this all went incredibly smoothly, so we really didn't see much impact at all. Yeah, so here is I'm not going to go through all of this in detail, but you can kind of see this is a kind of engineering, just some views of where various parts of the hardware actually are. So you can see kind of the primary mirror. So we have a few components that are within the instrument module. We have but then we have electronics, and then this whole compressor assembly kind of all the way down by the spacecraft bus almost. So the mid-infrared astronomy with JWST is like an incredibly powerful capability. So the plots you could see there are basically the atmospheric transmission in the mid-infrared. The top plot covers 6 to 14, the bottom is 16 to 28. So it's almost entirely the wavelengths covered by the MIRI instrument. And as you can see, so when these plots are high, it means a lot of radiation makes it down to the ground. But you can see here, for example, so this is the transmission of the Earth's atmosphere. So particularly here, the sort of 16 to 28, this is, this transmission is kind of a mess, and there's really not a lot of infrared light from space that can make it to the ground. So this wavelength range is largely inaccessible for ground-based telescopes. Not only does the atmosphere not let infrared radiation through, but the atmosphere itself radiates in the infrared. So it's something like, I think the flux from the atmosphere itself is something like 10 to the 9 photons per second at 10 microns. So having the space capability is extremely important. And MIRI's closest predecessor was not the Hubble Space Telescope, it was the Spitzer Space Telescope, which was a telescope whose mirror wasn't even a meter in size. So much smaller than JWST. And so MIRI's gains over Spitzer up to about 12.5 microns, where we're dominated by kind of astrophysical background, is about, it is a factor of about 50. At the longer wavelengths, Spitzer actually very quickly became confusion limited, so that the spatial resolution is so poor that you have this kind of background from sources itself. Because of MIRI's much higher spatial resolution due to the telescope being so much bigger, we will never really be confusion limited. And so even at the longer wavelengths where we actually operate at a slightly higher temperature, our telescope is at a slightly higher temperature than Spitzer was, it still means that we are getting a big increase in performance. And there is just nothing really, it's a huge step up from anything that was before, and there's nothing really on the horizon, nothing on the ground that will come anywhere close to MIRI's performance. So in that sense, it has a very unique capability, and something I'll come back to a few times. I think the potential for new science and scientific discovery for MIRI is actually very substantial.
Why does it have such a low spectral resolution? You said it is R equal to 100 or something?
The LRS is about 100. The medium resolution spectrometer is a few thousand, so it's about 3,000. But this is something that is difficult in space. At very high spectral resolution, your instruments have to be much bigger. And that is kind of a limitation you often get with space instrumentation. So the extremely high spectral resolution, where you're looking at 50,000, 100,000, that is more easily doable from the ground because you're not so limited by space. Okay, so I was going to show some highlights from commissioning. So here is sort of the timeline, the 6-month timeline for commissioning. So this kind of just shows you generally the phases that we saw. The deployment, the sort of travel out to L2 and deployment took up the first few weeks. And then all that time, the observatory would be cooling down passively. The commissioning of the telescope itself, so this is the primary mirror where we align and phase the mirror segments, that took up a good couple of months, 2 or 3 months in the middle. And in fact, that ended up being a fair bit shorter than had been anticipated because it just went so smoothly. And then the final period, the final few months, was all the science instruments. And so you can see this kind of was about where MIRI reached its operating temperature. So we were only really kind of able to start there, whereas the other instruments had done some of their functional activities. They had checked out that all the filter wheels worked, etc., by the time we, were even able to do any of those things. So we had a very, very densely packed period at the end where we kind of got all of our data. And you can see some of the things, some of the milestones on there. Some milestones in the telescope, getting the telescope working and properly aligned, different kind of tests that were run with the science instruments as well. This is kind of what the Mission Operations Center looks like in Baltimore. So during the 6-month period, we had to provide 24/7 support for every single subsystem over 180 days on 8 or 12-hour shifts. So this is even in the whole period where the science instruments were not yet being used and we were just for MIRI watching temperatures tick over. We still had to be there staffed 24 hours a day, 7 days a week. We also had daily status meetings 7 days a week. And then in addition to staffing the console and looking after the health and safety of the instruments, we also had to, once we got data, you then have to kind of provide the support to analyze the data and feed it back into the project to make sure everything is going well. So this was a very intense period of work.
What exactly are those people doing?
So every single subsystem has usually, like for us, for the instruments, we had a couple of desks. So these two people might have been working on, I think they were working on the telescope, but let's say they were working on an instrument. You have the various screens, and so you have big screens of telemetry, so where you are getting numbers down of every single sensor in your instrument. So this is temperatures, voltages, what it's doing, is it like every single sensor that's on there. So for us, it was probably about 200 or 300 telemetry points that we were constantly receiving.
Isn't it better done by computers though?
Well, we do pre-program a lot, like all the limits, for example, are sort of programmed in. So in reality, you're kind of, something is programmed to turn red if it is an unexpected value. So there is a lot of computing, computer development that goes into that. But we also have like a real-time console, so you could see at all times what was being run. What else were we doing? So you have access to the full schedule. We also are connected to voice loop, so we were talking on kind of headsets all the time, so you monitor what's going on. There were also, in preparation for an activity to be executed, there is various paperwork, like not actual paperwork, but like JIRA tickets. Basically, you have to file to say, I would like to start observation 5, 6, 7, 8, exposure number 5. I've checked it, it's ready to go. Everything has to be checked like 1 million times. That said, like I said, when MIRI was like just not doing anything, there was a lot of time where we weren't doing anything. So I can tell you all the things that had to be done, but there are definitely a lot of times when not a lot was happening for our particular instrument.
I guess at some level with an operation this expensive, there's kind of a feeling that there just have to be eyes on it all the time.
Yeah, and exactly, because particularly early on in commissioning, we did have a few safing events. So this is where something goes wrong and the observatory just shuts down. This is all usually just sort of completely in software, that it's programmed, like if this thing hits a limit, shut everything down and investigate. And then that means then after it's been shut down, every single system has to be brought back online, which is, for MIRI alone, that was about, 8, 9 hours, something like that. So so they want someone to be there, if something unexpected happens, it's, you have to be there to then be able to advise and say, our instrument is fine, we need to do this, that, and the other.
How long is the delay, like between the moment where you take decision and when it's actually done on the telescope?
So
Like,
basically,
light,
Yeah, light travel.
I mean, the actual light travel time itself, I think, is sort of, I keep forgetting the number, but it's like, seconds basically. But the whole, sending the commands, then there's some like software thing that happens, and there's overall it'd be some minutes basically, but it is very quick. So the mirror alignment, God, I'm running short of time. The telescope commissioning and the mirror alignment was like one of the coolest things. I wasn't really part of it. We were just watching this happen. So this was done by the engineers and scientists who worked on this were from Space Telescope Science Institute, also Goddard and Ball Aerospace, who Ball Aerospace built the mirrors. And so they had this whole procedure and all these algorithms figured out to get to that beautiful, finely aligned and phased point spread function. So when the mirror first folded out, all the segments are kind of pointed in random directions. None of them are aligned or anything. And so when you point that at a field, say you pointed at a single star, single isolated star, each and every one of the segments produces its own image. So you basically get like some hot mess of 18 points. And so that's what you can see here. So this is actually a little video.
So that's an image of a star when they first opened.
So this is actually a simulation, but the data. The point is like the data looked kind of exactly like this. It was extremely impressive. Only it wasn't a single star; it was a whole field. So initially, it's this whole field of stars, and each of them has like 18 images. So the first job that they had was to figure out which points you can see, which smudge matches with which segment. But they had this whole procedure where you kind of nudge a segment, see what moves, and then like, okay, this one is segment A1, this is one segment A2, and then you gradually kind of assign all of them, and then you can start actually building, putting them all in various positions. So I'm just going to play this, and you can see this happening. So you start off with these 18 dots, and they're not even round images because they're out of focus and they have some distortion. And so then each segment gets kind of tweaked, and then they see which of these spots actually moves. And then you start assigning labels to each of these spots. Then once you have them all assigned to a segment, you can then start moving them around. And then they had the software to basically compute exactly what commands need to go to what actuators to move the spots into that configuration that you see emerging now. And it really looked like this with the data. The videos that I have of the data were all like 10 minutes long, because they included a lot more. So I thought this was like a nice, simple demo. So this is like another view of kind of how they were all kind of that procedure happened and how they were then all stacked. So you had them in this hexagonal structure, and then each of the segments were also brought into focus. And then gradually, basically, they were moved for the spots to all be on top of each other. And that went through kind of various iterations.
So they keep them separate at first, just so they can focus them independently.
Yes,
I see.
exactly,
Okay.
exactly, yes. And it was sort of an iterative procedure, so they kind of went through that several times to kind of get everything very, optimally kind of phased as well. But there was actually time in the timeline to do this multiple times, and they found they didn't actually need to do that. So through the whole procedure once, and it was basically kind of worked really well. So this is then the image that was also released. This is the kind of optimally phased and aligned point spread function from the NIRCam instrument. This is before there was then a process to actually do it with all the instruments, so to get all the instruments at an optimal focus. That was then the next step after this. But as you can see, like one of the really spectacular things as soon as we started taking data is just the number of galaxies that appeared in the background. I mean, for this type of activity, we're looking at whoppingly bright stars. So these exposures are extremely short. And so even in these very short exposures, you have kind of hundreds of galaxies in the background. So that was, really spectacular during commissioning to be part of that. Once we got into science instrument commissioning, I'm not going to go through all of these in detail, but this is just like a list to show like how broad that those commissioning activities were. For every single instrument, we go from as simple as powering them on, reading out the detectors just to make sure we can read out the detectors, looking at a point source to make sure it looks like a point source, all the detector calibrations, flat fields, dark currents, things like that. Then to all of the kind of more sciencey calibrations like the wave calibration, flux calibration, etc. And so between the 4 instruments, there were 17 different modes of observation. So NIRCam alone has 10 individual detectors. So, this all takes a lot of time. There was a lot of complexity there. This shows, it's another image that was released. This is when the telescope was brought into focus for all, so when the mirror was phased and focused optimally for all 4 of the instruments. So you see these like beautiful star fields, and then in MIRI, because it has the longer wavelengths, you see like very different, you see all the extended emission popping out there. We looked at some beautiful targets during commissioning. So I know the fantastic images that were released in the middle of July, but really during commissioning we did some pretty spectacular observations. These, all kind of calibration targets, but these produced some beautiful data, and one of my teammates, Andras Gaspar, created some really nice views and comparisons with Hubble. So you see there an active galactic nucleus, NGC 6552, with Hubble on the left and with MIRI at 5 microns on the right. And so you really, the bright point source at the center is the active galactic nucleus, which is very bright in the mid-infrared. We also did the first test of a transiting exoplanet observation. So this is where we stare at the star as the planet transits in front of it. And as the planet comes in front of the starlight gets filtered through the atmosphere of the exoplanet. And so by comparing the out of transit and the in transit spectra, you can kind of measure the signatures of any molecules in the exoplanet's atmosphere. And that's going to be a huge area of science for JWST. These data were pretty spectacular because I think with previous missions to do these kinds of observations, you needed quite heavy processing to pull out the signal from the transit, because these are fractions of percent, these transit depths. Whereas with all 4 of the science instruments on JWST, it was kind of straight out of the pipeline. The transits were extremely evident, and we could get some detections of molecules even in there with very minimal processing. Here are just like some more beautiful images. We looked at the Cat's Eye Nebula, and this are views of the Large Magellanic Cloud through all of our different filters with MIRI. Okay. So these are some of the images from July, and kind of really highlighting kind of how unique the view in the mid-infrared is. So this is only the near-infrared, and then if the mid-infrared kind of shows such different structure, you really see the signatures of these shocks between those interacting galaxies pop out.
Can I ask you a question?
Yes.
If it is infrared, how do you put the colors on top of it?
Yeah, I mean, yes, they are. The colors are kind of artificial in that sense. So it is particularly for these like very spectacular PR images. We have a whole department at STSCI whose job it is basically to match the different filters with colors. But I mean, there is definitely a bit of a science to it, that you try to stay close to what things physically represent when they select these colors and when they make these images. But you're right, it's not real color.
Maybe this is how a frog would see it.
Do they see in the
Do they see in
infrared?
the infrared?
Well, if you have the 7
I
Kelvin
think
frogs.
from
Not 25 microns though, that's for sure.
Yeah, right, no, 7 Kelvin frog.
Yeah, exactly.
Let me skip through a few here because I have some like beautiful images we did. So Neptune looks kind of cool.
Jesus.
Yeah.
Neptune has a ring, people.
Yeah. And like that is Triton, right? The big point source next to it is actually Neptune's moon Triton. First detection of CO2 in an exoplanet atmosphere. Again, this took about like the main part of this analysis took about 3 days.
But I have to say, I mean, it might not be evident to people in the room,
Yeah.
but no exoplanet transits ever look like that.
So this is with the nurse. This is not
Yeah.
MIRI. This was with the NurSpec
Still,
instruments.
that
Yeah.
is ridiculous.
You mean the accuracy?
Yeah, just the beautiful image
Yeah.
there of the transit.
Not very much noise.
And then this is the wavelength dependence of that transit.
Yeah.
It's ridiculous.
CO2 is like a biosignature molecule. So this particular planet is not really a candidate for habitability, but it's the first time we do have a very clear spectroscopic detection of CO2 in an exoplanet atmosphere. So it's kind of a really important sort of pathfinder or step towards knowing that we can detect it at this level of precision in these atmospheres.
So, sorry, is it part of like your claim to fame that you guys will detect life or something? Or?
Careful.
I'd say no. I think generally people feel that JWST is not optimal to really kind of detect life. On the other hand, like I don't know whether we really know what we would even be looking for to find life. I mean, people like Hog and Dan over there might be able to answer that question better. But certainly we're going to I'm sure that we're going to make huge advances in understanding exoplanet atmospheres, how they form, what kind of conditions they have, and determining what habitability might look like. That I'm definitely sure of.
Can you
Got
see?
10 minutes, by the way, just
Okay.
to keep you on.
I was just going to ask, can you see methane?
Yes, I believe so.
Yeah, it should appear in the near infrared.
Right,
Yeah.
that's what I was thinking.
Has pretty strong infrared markers. Yeah.
And higher?
Sorry, is there something special about this particular exoplanet, or is this something you can in principle do for any?
So this observation was taken as part of what's called the early release science programs, which were kind of designed to return really good data to the community very quickly and very early on in the first cycle. So these data were taken with no exclusive access period at all. And the targets for these observations were taken sort of, they had to have like really good observability anytime during the year. And it was really, we wanted this to be like very, nothing like high risk, basically. So in that sense, there were, those were kind of the criteria, something that, an object that was fairly well understood, I believe, that was visible, and that there had already been hints that there would be some interesting things going on. So this had already been observed with Spitzer, so these points with error bars are Spitzer photometric points. These are the Spitzer filters here. So this kind of increase here, they had already been a suggestion that might be CO2. In that sense, I mean, it's a very interesting target, but it was also mainly chosen because we knew it would be feasible and it could yield very interesting results. And then to finish off, I was going to tell a bit of a story. Because this paper just got published, so it's also really nice to be able to highlight that. I believe this is the first science paper with the MIRI low resolution spectrometer, so that's exciting for me. So a team led by Saurabh Jha at Rutgers observed this type 1a supernova 2021 AEFX, and just published last week or beginning of this week, this beautiful joint spectrum starting from the SALT telescope, which is in South Africa, an optical ground-based telescope, all the way to 14 microns with MIRI, with also NIRSpec spectra in there, observed very early in cycle 1. And so this was led by Lindsay Kwok, who's a graduate student of Surabjaz at Rutgers. The reason, I mean, it's absolutely beautiful paper, beautiful data, but it was a bit of a journey for me, because I'm, the LRS lead. I do a lot of work on the calibration. But how this started is that we had, in the middle of July, updated all our calibration reference files, and we had very little time to really spend time with the data. We were under a huge amount of pressure to get this done. And so this is what the data first looked like. And so this arrived as a help desk ticket in my inbox in the middle of August, kind of going, oh, wavelength calibration is very strange. So we were looking at, so they flagged that we had errors in our wavelength calibration for the LRS of up to about half a micron, which is really bad. And this of course arrived the day before I was going on vacation. And so this was then, we had to kind of go figure out what on earth had happened. So how did that happen? So we can operate the MIRI LRS in 2 modes. So we have it with a fixed slit. So this is the imager detector, which has, this is the imager field of view. These are the coronagraph fields. And we have a fixed slit aperture here where the spectrum gets dispersed. When we do slitless spectroscopy, we have a little subarray up there that we use that we can read out really fast. The slitless mode, so if we read it out fast, because it doesn't have a slit, the sensitivity is poorer, but you can observe really bright targets with it for like exoplanet host stars. It's the exact same optical path, the exact same disperser, and it's a double prism, so it's 2 prisms. And it uses the exact same detector. Our dispersion, which we had measured from the ground and from an optical model, kind of looks like that plot in the top there. So you have pixels on the detector on the y-axis against microns. So it's kind of a weird shape, and it actually turns over onto itself, which does make it particularly, so it gets very, very steep at the short wavelengths, and then actually folds back onto itself. So it does make it a bit challenging. For the slit, we actually have a filter that blocks off everything below 4.5 microns. So that's also, again, a bit of a difference between operating in the 2 different ways. Now, the wavelength calibration it's kind of not that hard because it's just like a slit spectrograph. There's nothing particularly complex about it, but it was actually finding good targets was quite difficult because MIRI is so much more sensitive than anything before. So there were a lot of targets. The targets that were used in previous missions were all too bright for us, would just saturate immediately. Targets from the Hubble Space Telescope were fine, but that's quite a big distance in wavelength away from where we are. So we ended up having to pick targets that we had never actually seen mid-infrared spectra of before. And also at a resolution of 100, most lines are actually blended together. So it's very hard to get like sort of very clean line measurements along the spectrum that we could fit. And so we kind of assumed, or I kind of assumed that, again, from ground testing, when we did testing on the ground, we did not yet have defined our slitless subarray, the location of that. We had just plopped a source somewhere on the array and calibrated it. And based on that, we said the dispersion, so how the wavelengths are mapped onto the detector pixels is the same whether you operate it slit or slitless. And so we actually, from commissioning, only had 1 good target for wavelength calibration. The other one, because we didn't know for sure, just turned out to not have any good lines and we just couldn't really use it very well. But we were like, okay, that's fine because the dispersion is the same anyway, right? So, it actually turns out that, that was not the case. What's really nice is that, we do have, we do target acquisition and then we take an image once, so you can see here actually, there's a star in the slit. And so we take an image before we put the disperser in place. So we have a kind of pre-image. So right next to it is then what happens when you put the prism in and everything gets dispersed. So based on that, we were then able to figure out, finally, that the dispersion is actually not the same over the whole field. So depending on where you put the target, whether you put it in the slits or whether you put it somewhere else in the field, the dispersion is actually different, and quite significantly so. So this whole assumption that we had made of, the dispersion is kind of the same and we'll just apply one to the other was actually sort of completely wrong. And, and I'm the lead for the LRS and I have been for a decade. And in the end, it was a grad student at Rutgers who solved this problem. So it's kind of, I wanted to really talk about something that just didn't really work out all that well, and how we really benefited also from working with the community to improve the the calibration of our instrument.
That's a very strong endorsement, by the way, of the open science model.
Yeah, absolutely. Because actually, because we had a big to-do list of things we were working on, whereas this graduate student had a lot of time to work on it, and actually independently went to the archive, found a bunch of commissioning data, and figured out how to wavelength calibrate our instrument better, and then told us about it. And so we were then able to kind of improve a little bit more on it and update it for the entire community. And so it was definitely a case where, someone external having access to all of our data and being in constant communication with us as well, because we were constantly talking about this, kind of really accelerated how well our instrument was performing. Do you have a question?
Did you know that you had a calibration problem, or was there still a chance that there was a mechanical?
So we had tested it, and we knew that it wasn't great for the slits. So it worked really well. It worked really well for the slitless spectra. We knew that, and then we had applied it to the slit data, but because our slit data were just not great quality at that point. It was we think it is working. It seems to be a little bit less accurate, but it seems good enough. And we were just under so much time pressure to get things ready and updated before everything would be released to the community. We were just it's good enough, and we'll fix it later when we get more data. We hadn't realized how poor it actually was, and it wasn't until people started taking spectra of these things like these supernovae that have these big features that it really pops out, how terrible it was. So yes, it was a big exercise in open science and being very open in our communications and collaboration with the community as well. This has all been solved. It's all fine. We are getting more calibration data, so this is all getting improved. But it was a really big lesson for us on the team as well to sort of always question your assumptions and go back to basic physics, because it kind of is the angle of incidence on a prism does really impact the dispersion, and depending on where something is in the field, it does actually slightly impact what angle light is hitting your prism. So, and for me, I'm going to put this in there, and it's sort of, don't let your ego stand in your own way, because it was really hard for me as the lead of this mode to, have a grad student come and identify and solve a problem. So it's actually the first time I've told this story, but I thought it would be kind of interesting to kind of say that, and also it's going to be okay. That was a big. I needed people to tell me that as well at that point, because it's sort of, it's going to be all right. If you have a big problem, it's going to be fine.
Sarah, you are more or less out of time.
Mm-hmm. This is more or less my last slide, I think. Oh yeah, final slide. Of course, when we look at things like that, the really obvious question is, why are we not doing science with that data? Because right now we are not. This is not a mode that we support. But when you use the LRS in slit mode, you actually get all of the stuff in the imager field for free. And so this is kind of my top item on my wish list for future cycles, is figuring out how to calibrate that. Knowing what we know now, that the dispersion, the wavelength calibration is going to be slightly different at every point in the field. And so that is a fun project that I hope to be able to solve, problem that I hope to be able to solve. So that's something that I'm working on right now. But hopefully we can do a wide field slitless with the MIRI LRS. And that's it really. I'll just leave it with my summary.
Zhang asked online, what limits the lifetime of the mission?
So it was the availability of, so before launch, it was the availability of fuel. So we do need to make periodic course adjustments to keep JWST in a good orbit. That said, you know, the calculation of the amount of fuel that we had, there are very big margins, and there was a big dependency also on the accuracy of the launch, like how accurately can the Ariane rocket put us on that path to L2 and get us into that orbit. And as it turns out, that was extremely accurate, exceeding the predictions. So given that, with all the margins that were in there, we now know that the lifetime is going to be much more than 20 years even. So it is now, you know, we do now think that the lifetime may end up being limited by electronics or things like that.
So the fuel is no longer reasonable, is not really the limiting step, probably.
It might not be.
And the design lifetime is what, 10 years?
Right, so minimum was 5, the goal was sort of 10 years. So that's the thing, like everything on the observatory is kind of built for a 10-year mission. If we're now looking at sort of 20 to 2025, something of that order, then it's like, you know, things, you know, it's hard to predict, but it may not be the fuel that limits the lifetime. There may be other things that start to break first.
That's really great.
Why does it need fuel? Is it because the orbit is unstable, or is it because?
Yeah, so we need to make sort of small orbit adjustments to keep it in orbit. It's not like a fully stable orbit. No.
Yeah, it floats away, I think, if you don't constantly maintain.
Yeah.
Yeah.
So you two seem to be very proud of this open science. Can you say in a few words what exactly is that? In 2 sentences. Publish everything.
I think it's just sort of, you know, making as much data publicly available as early as possible. Making software open, like the JWST, the calibration pipeline, for example, all the code is publicly accessible. You know, kind of not hiding things behind, you know, even though it's, you know, a big NASA mission, we have the Space Telescope Science Institute who's building everything, but they actually have a really good culture of being extremely open about software. Even people in the community, you know, if Hug says, I think I can do this pipeline step better, he can go in and put in a pull request on GitHub, basically.
But normally people who fly telescopes have the first night or whatever rights, correct?
Yeah, so there is some guaranteed observing time for the people who build the instruments. The proposers...
And it does not contradict open science.
I mean, that is a very big question. Yes, there will be very different opinions about that depending on who you ask. It's actually a very big debate right now because there is a bit of a push from the US government that things should be made public sooner. And different observatories have different models for that as well. I think there is probably a balance you can find there.
Just to connect to that, the data that you showed where you said you haven't figured out what to do with it, how to calibrate it, is that now available? Can a PhD student start working on it?
So the I think the supernova spectrum that's published, I think I don't think that is public yet, but it has been published. All of the commissioning data, calibration data is public. So anyone can go download that, reprocess it, do whatever you want with it. There are also a number of programs that where the data is taken without any exclusive access, so that also becomes public from day one. And I mentioned the early release science program that showed the CO2 detection in the exoplanet atmosphere is an example of that. Those are specifically designed with zero exclusive access with a goal to release data from all of the different modes to the community, like immediately when they were taken, to help people learn how to work with the data and prepare for future observations.
One comment I would make about that is they were designed for the community to be able to learn, but in fact the teams learn as much as the community does.
Yeah, absolutely, yeah.
Interesting. Yeah.
Your timeline slide had like a circled bit saying the MIRI 3 weeks of terror. I was wondering what that referred to.
Yeah, so it's kind of just referring to the fact that because we were actively cooled, we had to wait a lot longer before we could start our commissioning activities. So we got something like, we got over half of our data only in the last few weeks of commissioning. So we spent months kind of twiddling our thumbs watching temperatures drop. And then we had this kind of like 3 weeks, I can't remember how many weeks it was. I think it was about 3, where we just had like every single observation was MIRI. And so we were just working round the clock to try and like analyze things, feed it back into new programs and things like that. So it was a very, very intense period for us.
One question I have is, the data come down from JWST through the Deep Space Network,
Yep.
right? So you need to share time on that network with the Mars missions
Yep.
and whatever other crazy things are happening. Does that limit the capabilities of the spacecraft and the observatory?
At times, yeah. So one big thing we've had in the last few months is Artemis. So this is NASA's, kind of mission to go back to the moon. Artemis has quite high bandwidth needs apparently, and so it depends on a lot of different factors, but there was at one point for the first launch, there was a sort of, it might reduce our contact time with the observatory to the extent where we had to, our scheduling department had to really put in place a lot of kind of low bandwidth, because we were worried that we would fill up our solid state recorders. Like if we can't get the data back from our telescope periodically, then we might fill up the solid state recorders. And
Meaning you store it in a buffer on board,
Exactly.
waiting until you have
Yes.
bandwidth, and then you take it down when you have bandwidth.
Exactly. And so the Artemis mission at some point was really threatening us being able to have contact with the observatory. I think at one point they even said we might not have contact for several days. And then we were like, well, because we only have about 60 gigabytes on board of storage. And it's like, well,
I think my phone crushes you.
I know, exactly, yes. So, there are aspects like that. And so with Artemis the launch getting scrubbed all of those times, like our scheduling department has had quite the challenge they're constantly reorganizing the schedule, and then the launch doesn't happen, so they have to roll everything back again to what it was. And so that happens.
Other questions?
There is one.
Yeah. Can NYU students apply for telescope hours? That's
Absolutely.
Jin.
Yeah, absolutely. So anyone from anywhere in the world can apply for time on JWST. Proposals are actually reviewed anonymously. So whether you're a student or a senior professor, your name will not be visible to the reviewers. That's specifically done to try and help kind of reduce any bias about that. And actually, since that was introduced for the Hubble Space Telescope, I think quite a few more very junior scientists have gotten time. So you absolutely have access. We have a ton of training materials online. The call for cycle 2 will be coming out in a couple of weeks' time with a deadline early next year. So and you're always welcome to contact the help desk. So if you Google JWST help desk, we are basically, that's part of our job, is basically to help you apply for time.
I hate to say it, I have to add that NYU physics graduate students have had time on the Spitzer Space Telescope and the Hubble Space Telescope, and lots of ground-based facilities. So in fact, one of the things that's great about astrophysics is you can have your own data as a student.
Yep. And if you're in the US, you actually get, if you have a successful proposal, you actually get a grant with that as well from NASA. So it actually comes with money.
Which your advisor will be happy to be the PI of. One last question. I think maybe Tim, you had a question? Last question?
Are there any serious proposals to turn the observatory to Earth? Or viable?
Well,
watch me sleep.
Yeah, I don't know. Well, I don't know actually. I don't think you would do that because then you would be pointing towards the sun as well, right? Because you're always along the line. So I don't think there's any way you can point to the Earth without also pointing at the sun. So it would not be good for the telescope.
But it is true that there's a lot of solar system work going on with the telescope.
Yes.
In fact, when they released an image of Jupiter, and I on Twitter was like saying, well, yes, I did know that Jupiter had a ring, obviously. Because it really clearly showed Jupiter's ring, which is actually quite hard to see.
Yeah, Yeah, I mean, some of the most spectacular data to come out so far has actually been from the solar system, I think. Yeah, beautiful.
But it's not a record holder in terms of angular resolution, right?
Sorry, it's not.
The angular resolution of this thing is not the record one, right? Some Earth 30-meter, whatever, probably are better, no?
Well, they don't exist yet.
They don't exist yet. I mean, VLBI, I think in the radio, the highest
Right.
thing it would be
Sure.
Event Horizon Telescope.
But you're saying currently this James Webb is the most resolving.
In the infrared, it's wavelength range.
If you push to 2 microns, I think it might be if you think
VLT?
about optical technology, well, VLT does interferometry. If you do pure optical technology, I think it is the best.
Yeah,
But if you allow interferometry, VLT
How
beats
big
it.
is the mirror? Sorry,
6.5 meters.
600.
Yeah. So
But
we do
no
have
atmosphere.
8-meter telescopes on the ground.
Right.
With adaptive
atmosphere.
optics, they can get. I think they can get quite close to the diffraction limit, but
So they do not get one because of atmosphere.
Yeah, and Strel ratio is bad.
yeah.
So I think it is better than anything. Of course, in the if you do interferometry, you can beat it.
Right, that's of course.
Yeah.
Was there a question in the back? Last chance.
Yeah, so if you wanted to observe the other half of the sky, you just have to wait 6 months.
I mean, it depends a bit. There's actually a software tool that lets you calculate the windows, like when a particular target, a particular location is visible and for how long. So it really depends on the ecliptic latitude of an object. But it is possible, yes. If you want to look at something, you might have to wait a few months for it to become visible to Webb. Yeah.
Okay, good. Let's thank Sarah again. And I firmly believe that there's some kind of reception somewhere. And I literally have no idea where.
Probably the SCSMR space.
I hope so, yes, that would be great. I should know the answer to that. I'm gonna not try.
Don't you have every week